Hi. Today's lecture we're going to pick up where we left off in class and discuss the section Herstein where he reviews Cauchy's theorem. Okay, so let's start by stating Cauchy's theorem. And we saw a version of this earlier in the semester. Cauchy's theorem says let G be a group and we're going to let n be the order of G, or the size of G. Okay? Sorry. Yes. Then if P divides n, where P is a prime number, then there exists an element A in G such that the order of A equals P. Okay? And we proved this already in the context of abelian groups. And the method of proof there was we looked at normal subgroups and quotients by normal subgroups and showed that, and kind of used an induction principle that if we knew that we had an element of order P in either the subgroup, the normal subgroup, or the quotient by the normal subgroup, then we had it in the larger group as well. Unfortunately, in non-abelian groups, you can't assume that any given subgroup is normal. So we have to have a different approach. And that approach is going to rely on something called an orbit. So we're going to let S be a set, and we're going to let F be an element of A of S, which, as you'll recall, is the group of bijections from S to itself. Okay, then suppose, so we're going to define an orbit. We say that for S in S, the orbit of S under F is the set of F to the I of S for non-negative values. Okay, so you have S when you apply the function when you apply the function 0 times, and then you have F of S, F applied twice to S, etc. So if we say, so this actually sets up an equivalence relation on S. We say that S is equivalent to T if T is in the orbit of S under F. Okay, and this will partition up the elements of the set S. Okay. Now we're going to prove a lemma about orbits. Say if F in A of S, remember that's the group of bijections, is of order P prime, okay, it's a group element, so it has an order, then the orbit of any element of S under F has one or P elements. Okay, so we know that F to the P is equal to the identity. So certainly this means that f to the p of s will be equal to s. Okay? So suppose that f to the k of s is equal to s for any k less than p. Okay? So let's say, if you apply f, so maybe our p is 5, maybe you apply f 3 times, then you get back to where you started. Well, if that's the case, then we can use, because p is a prime number, we can always find a and b such that ak plus bp equals 1, okay, where a and b are integers. But that means that f to the ak plus bp will be equal to of s will be equal to f of s, since that's just equal to 1, but we know that this is equal to, let's put the f to the 1 over here. F to the 1 of s is equal to f to the ak plus bp of s, which is equal to f to the ak of f to the, let me write it like this, f to the k to the a, composed with f to the p to the b applied to s, but each of these separately is the identity on s. So this is going to just be the identity. So it'll give you s as well. So that means that f to the 1 of s is equal to s, which means that the size of the orbit, so the size of the orbit is 1. Okay? And if f to the k of s is not equal to s for any k less than p, then we have the following elements. So we have s, f of s, etc., up to f to the p minus 1 of s. And this obviously has size p. Okay, so those are our two options. Either we have applying the function fewer times gives us s back, which means that the orbit has size 1, which we deduced over here, or each of the applications of f up to f to the p is distinct, which means the orbit has size p. Okay, so that's a bit about orbits, and now we're going to apply that to a special construction to prove Cauchy's theorem. And this proof was given by McKay well after the time of Cauchy, but it's a very elegant proof, and it goes as follows. So we're going to define S as lists of elements of G. Okay, so it's going to be lists of P elements of G, G1, G2, up to GP, with the special condition that the product of G1 through GP is equal to the identity. Okay? So the first thing we should do is convince ourselves that we can set the first P minus 1 elements freely, and then the last element is determined by the previous P minus 1. Right, so set G1 through GP minus 1 freely, and GP will be forced to be G1 through GP minus 1 inverse, just by virtue of the condition that we've placed on it. Its product has to be E. So because of this, the size of S will be equal to the size of G to the p minus 1. Okay, and we're calling this size of G n. Okay. So that's first. The second thing to observe is that if you have an element of the set given by G1 through GP, then we're going to act on this set by, well, let's first prove that the relevant element is actually an element of the set. So I'm going to claim that this implies that GP, G1, G2, etc. up to GP minus 1 is also in the set. Okay, and that's not hard to do either. So whenever you have x, y equals the identity, that means that yx is also equal to the identity. And you can see that by multiplying on the left by y and on the right by y inverse. And here our x is G1 through GP minus 1, GP minus 1, and our y is GP. Okay, so we're not relying on the abelian property here. We're just using a cyclic shift, and that actually preserves the product. Okay, so now we're going to act on S, this set of p tuples of elements of G, by shifting cyclically. By shifting G1 through GP to GP, G1, etc., GP minus 1. Okay? So this is, we'll call this element F. Okay, it's an element of A of S, and it sends this p tuple to the cyclic shift of the p tuple. Then what we're doing here, or what we note here, is that f to the p is the identity. Okay? Because once you shift from the end to the beginning, p times, you're back to where you started. So this means that the orbit of an element in S under F has size 1 or p by the lemma. Okay. Well, what does that say about this set? Well, we know that the set has size n to the p minus 1, as we deduced on the previous slide. But we also know that this is being partitioned into equivalence classes by these orbits. Okay, and so we have orbits of size 1. So it's 1 times the number of orbits of size 1 plus p times the number of orbits of size p. Okay? Well, we know that p divides n. So p divides n to the p minus 1. And we know that p divides this because you have a factor of p. So that means that the number of classes has to be, p has to divide that as well. P divides m1. Has to divide the number of orbits of size 1. But what that means is that, So if M1, P divides M1, we know that M1 has to be at least 1. Because we know that the element, which is just e's, when I do a cyclic shift, I just get the same element back. Okay? So this is an orbit of size 1. So I can't just say, oh, M1 equals 0. So M1 must be greater than or equal to P, which means that this implies that there's an element x not equal to E, which has x through x, also an orbit of size 1, which is in S. But that means that x to the P equals E, which is what we were looking for. Okay? Okay, so this proof is very beautiful. It involves a group action on a set that we defined by tuples of the group and tuples of group elements, and uses the divisibility of these different parts of the equation by P to deduce that we have these orbits of size 1 under that group action. It's a really lovely proof. So we can use this theorem to do a lot. The following results will build on Cauchy's theorem to deduce properties of groups of size PQ. And the first thing we're going to do is prove a lemma. Let G be a group of order PQ where P is greater than Q and both are prime numbers. If A in G has order P, the larger prime, then A, which is the subgroup generated by A, the cyclic subgroup generated by A, is normal in G. Okay, so how does this proof go? Well, we're going to claim that A is the only subgroup of order P. Suppose not. Then we would have another subgroup B of order P. B not equal to A is a subgroup of order P. Okay. We know that A intersect B would be a subgroup of both of them. So by Lagrange's theorem, the order of A intersect B would have to divide P. But that means it's either 1 or P. If the two subgroups are distinct, then we would require their intersection to have order 1, which would just be the identity. So that means that this is the identity. Okay, we're going to claim that the set of elements AB, meaning AB for A and A, and B and B, will be equal to, will have P squared distinct elements, okay? So this has to have P squared distinct elements. Okay, because if you were to take, let's say we have two elements in AB that are identical, so A1, B1 equals A2, B2, well then this means that A1, or rather A2 inverse A1 is equal to B2, B1 inverse. And we know that this is in A and this is in B. So the fact that they're equal means that they're in the intersection. So A2 inverse A1 equals B2 B1 inverse must be in the intersection. But that means it's equal to the identity, because the only element in the intersection is the identity, if we assume the groups are distinct. So that means that A1 equals A2 and B1 equals B2. So that tells me that any two elements in AB that are the same have the same corresponding elements in A and B. So that means that there are p squared elements. But there aren't p squared distinct elements in the group, there are only pq. So p squared is greater than pq since q is a smaller prime by assumption. And that means that we have arrived at a contradiction. So A is the only subgroup of order p. And that means that if we were to try and conjugate it, so x inverse AX, this is also a subgroup of order p. And that implies that x inverse AX must be equal to A for any x. Right? Because if A is the only subgroup of order p, that's where it's got to fall. And we know that this is the definition of normality. A is a normal subgroup of G. Okay. So that was cool. Now let's go to a corollary of that. Let G be a group of order PQ, P greater than Q both prime. If A and G has order P and X is any element in G, then X inverse AX equals A to the I for some 0 less than I less than P. So if we take, obviously we just proved that X inverse AX equals A, and we know that A equals the set of powers of A, so, from A square A to up to A to the P minus 1. Okay. So all we have to show really is that X inverse AX is not equal to the identity. And this is, so suppose this were true, then multiplying by X on the left and X inverse on the right, you get A equals E, which is obviously not true if A has order P. So that means that X inverse AX is one of these other elements, and that's just A to the I for I between 1 and P minus 1. Okay. All right, let's do another lemma. We're building up to a nice classification result, so please bear with me. Let A and B in G have orders O of A equals M and O of B equals N, with the greatest common divisor of M and N being equal to 1. Suppose also that A and B commute. Then C equals AB has order Mn. Okay. So the first thing that we'll note is that if we let A be the subgroup generated by A and B will be the subgroup generated by B, then A intersect B has to have order that divides both M and N. Okay, but because these are relatively prime, that means that the intersection must have order 1, which means that it's equal to the identity. Right? That's the only subgroup of order 1. So we have A intersect B equals the identity. Now let's consider C equals AB. And suppose that c to the k equals the identity, that means that a to the k, b to the k equals the identity because, as we recall, the elements commute. That means that a to the k equals b to the minus k. And this means that because these are both in, this is in, the left-hand side is in A and the right-hand side is in B, that means these both must be equal to the identity because that's the only element that's both in A and in B. Well, we know that A has order m, so that means that k must divide m. Okay, and the same process, if instead we multiply by just take the inverses, so k must also divide n. But that means that, I'm sorry, the other way around. M must divide k because if some exponent gives you the identity, that means the order divides it. And similarly, n divides k. Okay, but because m and n are relatively prime, that means that mn must divide k. All right? And that gives us c to the mn equals the identity. Okay? Because mn both divides k, so because any exponent for which this works has mn as a factor, that means that mn will be the smallest integer achieving this, so that's the order. Okay, now we can prove our theorem. Let G be a group of order PQ with P greater than Q, and both are prime. If Q does not divide P minus 1, then G must be cyclic. Okay, so we're going to use all of the results we've proved so far. So we have P greater than Q, so we're going to have a normal subgroup. So Cauchy's theorem implies that we have an A of order, there's an A and a B in the group where A has order P and B has order Q. Okay? So we know from the later results that if we take any element, if we take A and we conjugate it by any element in G, what we're going to get is A to the I for some I between 0 and P minus and P. Okay. So from one of the later results, we saw that B inverse AB is going to be equal to A to the I for some I between 0 and P, right? And this is actually a result we proved in one of the problem sessions earlier by induction, that this implies B to the minus R, A, B to the R equals A to the I to the R for all R. And because this is true for all R, it's true for Q. But when we plug in Q, we know B to the Q is equal to the identity. So that means that for R equals Q, this tells us A equals A to the I to the Q. Okay? So what that means to us is because A has order P, I to the Q must be congruent to P to 1 mod P. So we know that I to the P minus 1 is congruent to 1 mod P by Fermat's little theorem, which we proved using the multiplicative group of units. So we know that Q is prime, and it does not divide P minus 1, so that means that these two numbers are relatively prime. And that means that we'll have AB such that AQ plus B times P minus 1 equals 1. So that means that, again, because I to the Q and I to the P minus 1 are both congruent to 1 mod P, that means that I to the AQ plus B times P minus 1, which is just equal to I to the 1, well, that's going to be equal to I to the Q to the A plus I to the P minus 1 to the B, times I to the P minus 1 to the B, which is just equal to 1 times 1, or 1. So that tells me I is 1, which means, recalling what I was, that B inverse AB equals A. But that means that AB equals BA, which means they commute, and we just proved a result for commuting for groups where the generators of these subgroups commute, which says that that C equals AB has order, in this case PQ. Okay. But that means, because that's the order of the group, that means that G is just equal to the cyclic group generated by C. Okay? And that proves our theorem. What happens if Q does divide P minus 1? So that was something that we stated as a condition here. Q can't divide P minus 1, and that's what allowed us to deduce that I was equal to 1. Well, consider, for example, P equals 5, Q equals 2. So in this case, 2 does divide 5 minus 1. And indeed, so let's take an element A of order 2, A of order 5, and B such that O of B is equal to 2. And we're going to conjugate A and see what values of I are valid here. Well, how many different values are possible? We know that I is going to be 1, 2, 3, or 4. And we know that we can raise this, we can take B to the minus R, A, B to the R equals A to the I to the R. So let's set that equal to, because B has order 2, we'll set that R equal to 2, which means that A is equal to A to the I squared. In this case, I squared, so that means I squared is congruent to 1 mod 5. But looking at our possibilities, so I squared, that means that I has to be equal to 1 or 4, because for 2 and 3, I squared is 4. So I would be equal to 1 or 4. So if I is equal to 1, that means that A and B commute. But if I is equal to 4, that means that we have the relation B inverse AB equals A to the 4th. And indeed, this is a valid description of a group, specifically the group D2 times 5, the group of symmetries of a regular pentagon. Okay, so it's not really a regular pentagon, but we do our best. and this is not a cyclic group, and it's not an abelian group. So this condition that Q does not divide P minus 1 is absolutely essential for that result. Okay, thanks for your attention.